Hey everybody, so far in this unit of equilibrium, we've learned about the collision theory. That's how reactions occur. Two molecules need to collide in the right direction with the right amount of energy. And we've also learned that chemical reactions are reversible. Now what we're going to do is put those two things together and be able to apply LeChatlier's principle. So LeChatlier's principle states in simple terms, if you mess with the system at equilibrium, it will fix itself. Now, where this came from originally was when scientists were trying to make ammonia. Ammonia is NH3. It's a gas. And the things that make up ammonia are hydrogen, which we find in the atmosphere, also a gas, and nitrogen, which is found in the atmosphere, also a gas. When we go to balance the equation, we need a 2 and a 3. So, scientists said, hey, we should be able to make a lot of money if we can make some ammonia. So let's mix together some hydrogen and some nitrogen and make some. And everybody thought that was a great idea. They try it out and they get a really crappy percent yield. Like a really, really bad one. Like maybe 5%, 10% is it. So they say, well, that's not going to work because, what's wrong with this? Maybe it's our reaction conditions. I don't know. And they find out that actually this is a reversible reaction. So then scientists said, what can I do to force this reaction to go in the direction that I want? What can I do to prevent the ammonia from breaking down and actually force the hydrogen and nitrogen to react to form the ammonia in the end? And that's the basis of LeChatlier's principle, is we've got these reversible reactions. We're going to change the reaction conditions and figure out which ways the reaction shifts as a result of these changes in the reaction conditions. So the official definition of LeChatlier's principle is this. LeChatlier's principle states that if an external stress, so if we mess with something, if we stress this system of a reversible reaction, if we stress a reversible reaction, then the system will adjust itself to get relief. So that's LeChatlier's principle. Now, what kind of stresses can we put on a system at equilibrium? Well, it's easy to mess with concentrations. So we can mess with concentrations of these different things in the chemical reaction. We can change the temperature very easily by putting a reaction vessel like a beaker or a test tube in an ice bath or heating it up. We can also adjust pressures of reactions of gases. Last, we could add a catalyst. So we're going to go through each of these individually right now. First one is changes in concentration. Here's the premise. If we add more stuff in, then that stuff is going to need to be used up. So we will push the reaction to the opposite side. If we take stuff out, so we lower the concentration of something, then it will need to be replaced because, again, these systems are adjusting themselves to relieve the stress. And the result is pulling the reaction to the same side. So here's our reversible reaction. And let's say we stress this reversible reaction. The stress that we're going to do is we're going to increase the amount of A. Well, here's A on this side right here. So we're increasing A. If the stresses to increase A. The question on the table is, which way does the reaction shift? Does it shift to I'm left-right deficient. Here's left, here's right. Does it shift to the left? Does it shift to the reactant side? Or does it shift to the right? Does it shift to the product side? Well, here's the stress. We're going to increase A. Here's the relief. The relief of increasing A is to get rid of it. That means the reaction is going to be pushed to the opposite side of A. The opposite side of A is the right. So we will push the reaction to the right. If we increase the A, we need to get rid of it. So the reaction shifts all the way to the right. The effect of that is going to be to use up more B and cause more C and D to form. We're shifting again to the right because that's the opposite side of A. Second example, what if we remove D? So here's D right here. If we remove D, the relief would be to replace it. If we're trying to replace D, then that means we're going to pull the reaction to the same side as D. Since D is on the right, we're going to again shift the reaction to the right. The effect again is we're going to cause more C and D to form. We're pushing the equilibrium towards products, which is also another word for the right side of the equation, because D is a product. So that's the changes in concentration. Next, we've got changes in pressure. If we're looking at changes in pressure, the rule is one or more reactant or product has to be a gas. We've got our reversible reaction, where we've got our two arrows instead of boxes. And in this equation, we have 2 molecules of NO2 going to 1 molecule of N2O4. If I rewrite this with the correct subscripts, looks like this. 2 molecules of NO2, and that's a gas, added to... Oh, whoops, we're not adding to anything. We're just doing our arrows that are double-sided. Double-sided arrow, because it's a reversible reaction, going to N2O4. Also a gas. So, if we're messing with pressure, pressure only matters if we've got at least one gas in the equation. In this equation, we have 2 gases. Notice that we have unequal number of molecules or moles on either side of the equation. There's 2 moles on the reactant side, only 1 mole of gas on the product side. So again, just to emphasize that, we've got 2 moles of gas on the reactant side, only 1 mole of gas on the product side. If the stress is that we're putting on the system, so we've got this reaction going on in a sealed container, if we increase the pressure, that's exactly like lowering the volume. Because remember from our gas laws unit, pressure and volume have an indirect or opposite relationship. So if we increase the pressure, then we're smashing down the volume. The relief that this chemical reaction will need to go through is to make more room. And what makes more room? What takes up more space? 2 molecules or 1 molecule? Well, 1 molecule does. So the side with fewer moles of gas will be favored. It'll shift to the right in this case because on the right side we have only 1 mole of gas. Second example, if we decrease the pressure, then the reaction will respond by trying to take up more space. So the side with more moles of gas will be favored. And the side with more moles of gas is the left side, the reactant side. And that's our changes in pressure. Next, we've got the effect of temperature. And the effect of temperature is heat is going to act just like a reactant or a product. If we add more, it'll need to be used. If we take it away, it'll need to be replaced. First, we'll need to figure out what side heat is on. And by the way, our value of K will change because K depends on temperature. So here we have a chemical equation. We have two lead 2 sulfide solid molecules added to 3 oxygen gas molecules. We have our double-sided arrow going to 2 lead 2 oxide solids plus 2 sulfur dioxide gases. And here's the information that we're given is our delta H value is negative 827.0 kilojoules. The information that you're given tells you which side the heat is on. Since delta H is negative, the reaction is exothermic and heat is a product. So heat goes over here on the product side of the equation. Here's our second example. We've got lead 2 oxide plus solid carbon going to lead solid plus carbon monoxide gas. Our delta H value is positive. When delta H positive, reaction's endothermic and heat is a reactant. So heat goes on the reactant side of the equation. Here's an example of LeChatlier's principle. The stress is we're going to add heat to the second equation. So we're going to take this equation, the second equation, and heat it up. So we're upping the temperature of this second equation. It's taking place in a container, and we're putting that container in the oven. The relief that the reaction will need to go through is to cool it down, take away the heat. Since the heat is on the left-hand side of the equation will need to move to the right to get rid of the heat. So it'll need to use up the heat and move to the right. There's our example of temperature. Last, we can mess with the catalyst. And catalyst is a trick question. Equilibrium will not be affected. Because a catalyst affects speed only at which the forward and reverse reaction occur, the catalyst will lower the activation energy needed for both the forward reaction and the reverse reaction. And no net effect will take place. Everything will just happen faster, but at the end of the day, no change will occur. Try this out. So try out, here's our equation up here at the top. We've got AS406, let me rewrite it. AS406, which is a solid, adding to 6 carbon atoms, which is a solid. Here's our reversible reactions going to AS, 4 of those bonded together, plus which is a gas, plus 6 carbon monoxide gas molecules. Try out these different simulations. So which way is the reaction pushed when each of these happen? Pause the video now, try it out, and then come back for the answers. Okay, so you're back. Carbon monoxide is added. Carbon monoxide is on the right-hand side of the equation. When a substance is added, it needs to be used up, so the reaction will be pushed to the opposite side, left. If carbon is added, well, carbon's on the left side of the equation. Since carbon's on the left side of the equation, we're adding it. We'll need to push it to the opposite side. That's right. If carbon is removed, it'll need to be replaced. Since carbon is on the left side of the equation, if we need to replace it, then everything will shift to the left side of the equation. If As4O6 is added, it will need to be used up. In order to use it up, we push the entire reaction to the opposite side. The opposite side is right. If we remove As4 is on the right side of the equation. Since we're removing it, it'll need to be replaced. How we replace it is by shifting the entire equation over to the right. If we increase the pressure, the side with the fewest gas molecules will be favored. Since there's no gas molecules on the left, that's the side that will be favored. There's 7 gas molecules on the right. So if we increase the pressure, 0 is less than 7, the reaction shifts to the left. Last, catalyst, no change. Trick question. And there's our LeChatlier Notes.